A very good morning to all. Welcome back. In this session, we are going to discuss one more sorting algorithm which is called as the insertion sort. So, by looking at the name itself, we can get an idea of what insertion sort is going to do and how it is going to be implemented. Insertion. So, you are going to insert an element at the correct position. This is the basic idea. This is the basic idea, but we will extend the basic idea. So, as we have seen in the earlier session about the selection sort, where we are going to divide the given list of elements into two groups. One is the sorted group and the second one is the unsorted group. Initially, we will take all the items in the unsorted group and the sorted group will be empty. And when you start implementing the procedure of the insertion sort, we will move the elements from the unsorted group to the sorted group. So, the sorted group becomes more and more and the unsorted group becomes compressed. And coming to the basic idea or the procedure behind this insertion sort is very important. So, the basic idea is pick an element from the unsorted list and compare it with the elements ahead of it. This is very important. So, you take an element and you have to compare that element with the elements ahead of it. This we will see it with an example. This is the actual idea behind the insertion sort. Pick an element, compare it with the elements ahead of it and then insert the item at the right position in the sorted group to maintain the sorted property. So, once you pick the element, compare it with the previous elements and you have to find the right position, and when you find the right position, you make a gap over there and then place the element which you have picked in that position. And this process has to be repeated until the elements in the unsorted group becomes empty, or you can also say like this also. You have to repeat the process until all the elements become sorted. So, with the idea in your mind, with this basic idea of the insertion sort in our mind, let me discuss the characteristics of insertion sort. Before illustrating with an example, let me discuss the characteristics. As we have seen with the earlier sorting mechanisms like the bubble sort and the selection sort, which are very simple to understand and which are very simple to implement, this insertion sort is also the simplest algorithm we have. The implementation is simple, the logic what we can understand from this insertion sort will be also very simple, easy to understand and easy to implement. And one important, very important property regarding this insertion sort is it is efficient for smaller data sets, but very inefficient for larger lists. So, never ever consider the implementation of insertion sort when you have large list of elements. Even the bubble sort and the selection sort is also suitable for the smaller list of elements only. These points are very important. So, the bubble sort, the selection sort and the insertion sort, they are efficient when you have smaller list of values. When you have larger list of values, we have some other algorithms like the quick sort or the merge sort, which is very difficult to implement, but it is very efficient than these sorting algorithms. So, keeping aside all these things, just remember that the insertion sort is best suitable for smaller list of elements, and the insertion sort is adaptive in nature. Adaptive means it will adapt to the conditions. For example, if you have a sorted list of elements, not exactly all the elements are sorted, let me tell you that, let me take the list of elements which are partially sorted. That means, some of the elements are in their positions, actual positions, but some of the elements are not in their actual positions. So, we can say it as a partially sorted list. When you take a partially sorted list, its efficiency automatically increases. So, you can also keep it in mind that insertion sort will be the best sorting algorithm if you have some of the elements which are already sorted, or it is the best efficient algorithm. The insertion sort will be the efficient algorithm when you have partially sorted list. This is very important Viva question or interview question, whatever it may be. You may be asked a question like, what is the best sorting algorithm if you consider a partially sorted list? Undoubtedly, you can say that it is insertion sort. So, that property we are calling it as the adaptive property, and it is better than the selection sort and the bubble sort, because it is stable in nature. The stability of the insertion sort makes this sorting algorithm better than the selection sort and bubble sort. What do I mean by stability? Means when you have the equal keys, you are not going to disturb their places, or you are not going to implement the swap. But when you consider the selection sort algorithm or the bubble sort, if the elements are equal, if they have the equal keys, then also you are going to implement the swapping mechanism. But here we are not going to change the position or the relative order of the elements with the equal keys. That is the reason why we call it as the stable sort algorithm, or it is stable in nature. Because of this stability, because of this stable property, the insertion sort is better than the selection sort and bubble sort. And one more advantage with this insertion sort, or one more characteristic, best characteristic of this insertion sort is its space complexity is very less. It is not going to take more and more space. Actually, it takes only big O of 1 space complexity. What do you mean by big O of 1? Means you are going to take only one space in the sense to accommodate only one element. So, the additional space what you require for this implementation of the insertion sort is one space which can accommodate one element, that is it. So, the space complexity is very less, and we can say this property of having the additional memory space as big O of 1 as the in place sorting algorithm. So, this insertion sort is an example of in place sorting algorithm also. You may be asked a question, give me some examples of in place sorting algorithms. The best example is insertion sort, and it is online. Another property of this insertion sort is online. What I mean by online means you can sort the list of element as it receives. So, on the fly, you can also say it as on the fly. There is no need to take an array and insert the elements inside the array, store it. This is not necessary. When you are working online or when you are working in a condition where you are going to take the elements on the fly, in that situation also you can implement this insertion sort. Very important property. Because of these characteristics, we can say that the insertion sort is better than the selection sort and bubble sort. It is not the best, it is better than the selection and bubble sort. So, let us see the properties again. Very simplest algorithm to implement, works very efficiently on smaller data sets, it is adaptive and space complexity is very less, stable, online, in place, all these are the characteristics. Let us illustrate the insertion sort with one example. So, this is the list of elements that I have given. It is an array. So, I am giving the array index for proper understanding of the concepts. The array index starts with 0 and ends with n minus 1. So, in this particular scenario, I have the array index as ranging from 0 to 11. These are the unsorted list of elements. Initially, we take the given list as the unsorted array. All the elements of the list will be considered to be under unsorted array. And then, when you go on implementing the insertion sort, you will move the elements from the unsorted array to the sorted array. That is it. The implementation is somewhat difficult to understand. Why? Because in the bubble sort and the selection sort, you are starting your procedure from the first element onwards, and comparison is towards the right hand side. But here it is a reverse case. See here, you are not going to start the insertion sort with 0th element. This element is not considered for starting of your insertion sort. So, 40 is eliminated. Now you are going to start your process with the second element, that is a of 1, that is 2. The basic idea, let us remind or recollect what is the basic idea behind this insertion sort. You pick an element, compare it with the previous elements or the elements ahead of it, and insert it at the correct position. This is the basic idea. With that basic idea, why we are not considering this 40 means there are no elements before 40. So, there is nothing to compare if you take the first element for insertion sort. That is the reason why we will start the insertion sort with the second element. So, it is a simple case. In all the previous cases, you will try to loop or you will start the looping from I is equal to 0th index. But in the insertion sort, you will start it with for I is equal to 1, that is it. Very simple change in the program you are going to do. This is for insertion sort, this is for remaining sorting algorithms. Right. You consider the A of 1 element and you compare that element with the elements ahead of it. So, 2 compared with 40. Since 2 is less than 40 and again there are no elements ahead of 40 to compare. So, what you have to do? The correct position of 2 is in this position, this one. You have to insert it. Remember that you are not going to swap, very important point. The insertion sort works on the principle of inserting the element at the correct position. You are not going to swap it. So, insertion means you have to create a space here. So, for creating space, what we will do is, we will take an element, here, we will copy 40 here. Let me take the element as some x, x will be 40. Now, we have created a space at this position. You can copy or you can insert 2 into 40. Here in this particular scenario it appears as if it is swap, but when you go through the example we will actually find what is happening. We are not going to swap the elements, we are going to insert the element. So, 20 is copied into this empty location, initially it is empty, right, 40 is copied. So, 20 is replaced with 2 is replaced with 40, like this. Now, you will copy this 40 with this one. So, it becomes 40. It becomes 40. This is the position after making necessary changes or after implementing the insertion sort for the first iteration. These two elements are considered to be sorted array, and from here to here the end, these are considered as unsorted array. Now, we will repeat the process. You take the third element, that is a of 2. Now, you compare 1 with 40. It should be 1 should be before 40, right, but there are still more elements. 1 compared with 2, 1 should be before 2, okay, but there are no other elements to compare at this ahead of 2. In this position, I have identified the correct place where I have to insert 1, that is before 2. For this, what I have to do? I have to create a space at this location. This is my position where I have to insert 2. I have to create a space, but I should not disturb this order. So, for this purpose, what I am doing is, I will copy this x, I will copy the element 1 into x, and then I will move this 40 towards its right hand side and 2 towards its right hand side. So, what happened here? This 1 is replaced with 40 and 40 is replaced with 2. Now, I have created a space here, I have to insert that one. So, you replace this 2 with 1, this is what I will get here, 1, 2 and 40, this is the sorted array, and 43 to 4, this is unsorted array. Let us repeat this for our understanding purpose. Now, the next element what I have to consider is the first element in the unsorted array, that is 43. Okay. Compare 43 with the elements ahead of it. Okay. So, 43 compared with 40, since 43 is greater than 40, there is nothing to do. So, you leave this 43 as it is. Since it is stable, you are not going to change the position or you are not going to swap the position, right. After this, this is sorted array and this will be unsorted array. Take the first element of the unsorted array, compare it with the elements ahead of it. So, 3 compared with 43, it should be before 3 and again compare 3 with 40, it should be before 40, and when you compare 3 with 2, it should be after 3. So, the correct position of 3 will be after 2 and before 40 here. At this position you have to insert. To insert 3 at this position, you have to create a space at this location. So, to create space, you have to move all the elements after 2 towards its right hand side, one position towards its right hand side. So, for this what you will do? You will take a variable and copy it, the element, copy the element 3 into x, and then you try to move all the elements one position towards its right. So, 43 moved to this position, now 40 moved to this position is vacant. So, you insert 3 here. Now, the elements will be 1, 2, 3, 40 and 43. This is sorted and this is unsorted. Take the first element of the unsorted array 65, compare it with the elements ahead of it. 65 compared with 43. Since 65 is greater than 43, nothing to do, leave it. And after this step, this becomes sorted and this becomes unsorted. Now, the first element of the unsorted array is 0. Now, you can understand how it is going to happen very clearly. Take 0, that means you are picking up an element as 0, compare it with elements ahead of it, compare it with 65, it should be before 65, compare it 43, it should be before 43, compare it with 40, 0 should be before 40, compare it with 3, 0 should be before 3, compare it with 2, 0 should be before 2, compare it with 1, it should be before 0. There are no elements here. So, the correct position where you have to insert this 0 will be at this position. You have to create a space at this location. For creating space, you are not going to swap, very important point, never swap in the insertion sort. It entirely depends on inserting the new element. So, for creating space at the first location, you have to move all the elements after this 0, that means 1, 2, 3, 40, 43, 45, you have to move it towards its right hand side one position. So, 65 moved here, 43 moved here, 40 will move it here, 3 will move it here, 2 will move it here and 1 will move it here. So, at this position I will get the elements as this becomes 65 and this becomes 43. This one is 43 and this becomes 40, this is 3, this is 2, this is 1 and here you have a vacant space. So, before moving what you will do? You will copy it, the element should be copied to x and then you insert the element here. After this step I will get the elements as here, this like this. This is sorted and this is unsorted. Now, we will repeat the process. Take the new element as -1, compare it with elements ahead of it, -1 compared with 65, 43, 40, 3, 2, 1 and 0. So, -1 should be at this position. You have to create a space here. For creating space, you have to move all the elements towards its right hand side one position. Like this. Before this, what I have to do? I have to take a variable and I have to copy the value of unsorted array here, x is equal to -1. Now, the new element becomes, it becomes 65, it becomes 43, this will be 40, this will be 3, 2, 1, 0, here I have a space. Now, I just insert this -1 here, this is what happens, result. After that, we have 58, compare it with the elements ahead of it, 58 compared with 65, it should be before 65, when you compare 58 with 43, it should be after 43. So, the correct position of 58 will be between this 43 and 65. So, you take x value as 58, move 65 towards its right hand side, now it becomes 65 and now this is a vacant space. You insert this 58 here. After this I get the list like this. Now 3, compare 3. 3 compared with 65, 58, 43, 40 and 3 should be before 40. Now, you just look at the scenario here. 3 compared with 3. Since both are having the equal keys and since it is adaptive in nature and it is stable in nature, you should not disturb this element. The elements with equal keys will not be disturbed, they retain their position. This is what we have learned in the characteristics of insertion sort. So, the new element which you are going to insert should be after 3 and before 40. So, this is the correct position where I have to insert. So, I have to create a space here. For creating a space, I copy this new element into another variable. I move all the elements element by element towards its right hand side. So, this is 65, this is 58, this becomes 43 and this becomes 40. Here I have a space here. Insert this element here, that is it. So, the new list will be this one. In this scenario, what you have to understand is when you have equal keys, you are not going to disturb the already existing position of the key, of the element. So, we are not going to disturb this 3. Right. Now, 42. 42 compared with 65, compared with 58 and compared with 43, the correct position is at this position, at this location. I take x, copy 42 into x, move these elements towards its right hand side. This becomes 65, this becomes 58, this becomes 43 and this is 40. Sorry, here the space has been allocated and you insert this 42 here, this one. Now, the last element 4 compared with 65, compared with 58, 43, 42, 40, compared with 3. The correct position of 4 will be in between this 3 and 40. I have to create a space here. For creating a space, the first step is you copy that element into a variable, move all the elements one position towards their right hand side. This becomes 65, this is 58, this is 43 and this is 42 and this is 40. Here I have a space, insert this element here and after this you can see all the elements are sorted. So, you have to stop your procedure. So, picking up an element, comparing it with the adjacent, not adjacent element, sorry, picking up an element, comparing it with the elements ahead of it and inserting it at the correct position should be repeated until all the elements are shifted from the unsorted array to the sorted array, or you can also say that if all the elements get sorted. So, this is the end of the insertion sort procedure. And coming to the analysis part, the insertion sort, we have the worst case analysis as big O of n square. And the best case analysis is big O of n. What is this worst case and the best case? So, when you consider the insertion sort, the worst case is a scenario where all the elements are in the unsorted array, are in the unsorted manner. Every element you have to move its position, or every element you have to insert it to its correct position. What do you mean by best case? Means the list of elements are partially or almost in the sorted order. In such case, we are not going to disturb the position of the already sorted element. So, in such scenario you will get the best or the efficient insertion algorithm. So, that is the case which we are calling it as the best case. So, the best case is almost sorted order or sorted list you will take, whereas the worst case is complete or the entire list of elements will be complete unsorted list. When you take the complete unsorted list, we will get the time complexity as big O of n square, and if you take almost sorted list, we will get the best case or the time complexity as big O of n, which we are considering it as best case. Let us have a quick recap of what we have discussed in insertion sort. The basic idea we have discussed, which is nothing but pick an element, compare it with the elements ahead of it and insert that element in the correct position. This process we have to repeat it until all the elements get sorted. After that, we have seen some of the characteristics of insertion sort, like it is very simple to implement, stable, online, adaptive, better than the selection and bubble sort, all these things we have seen. And then we have illustrated the implementation of the insertion sort with an example list of elements. Remember, very important point, in the insertion sort we are not going to perform any swap operation, we are going to perform the insert operation. So, for performing the insert operation, you have to create a space over there for its correct position. When you want to create a space, you have to move all the elements towards its right hand side one position. So, you will move it and then you create a space and then you insert or copy the unsorted element into its correct position. And finally, we have seen the complexity or the analysis part of the insertion sort, where in the worst case we have big O of n square and in the best case we have big O of n. That is all for today's session. Thank you one and all for joining the session.